The story of stars begins long before the first astronomer tilted a bronze instrument toward the night, long before the first myth tried to place the glittering pattern of the heavens into the logic of gods and beasts, long before humankind even learned the art of fire. To understand stars historically is to step into a lineage that stretches back not centuries, but epochs, into a time when our distant ancestors raised their eyes and saw not points of light, but a mysterious, trembling map whose symbols they could feel, even without knowing. The earliest traces of humanity's wonder toward these lights are carved on the walls of Paleolithic caves, where clusters of dots near depictions of animals may represent the Pleiades or other familiar constellations, silently testifying that long before written language existed, the connection between star and story had already begun to form. As groups migrated across continents, they carried with them primitive memories of seasonal skies, recognizing familiar shapes as loyal markers that followed them through the wilderness and across the shifting millennia. The ancient world, as it dawned, inherited this fascination and amplified it beyond simple recognition, transforming stars into guides, clocks, calendars, omens, and instruments of fate. In Mesopotamia, the cradle of recorded civilization, priests of the ziggurats kept meticulous clay tablet archives of stellar appearances, charting the heliacal rising of Sirius and the wandering paths of 5 planets whose serpentine motions demanded explanation. These astronomer priests, the Umanu, observed the sky not for beauty but for necessity, interpreting stellar behavior as messages from divine realms. Each star belonged to a deity, and each shift in brightness or position carried significance for kings and empires. Through centuries of watching, they identified constellations such as the lion, the bull, and the scorpion, shapes that still linger today, fossilized in our modern zodiac, even after the civilizations that first imagined them faded into dust. To the people of Ur and Babylon, stars were neither distant furnaces nor cosmic giants, but living symbols whose whispers shaped the fortunes of cities. When Egyptian civilization rose on the banks of the Nile, the stars wove themselves into an entirely different narrative, one of cycles, resurrection, and the rhythm of the river that sustained life. The Egyptians recognized Sirius, known to them as Sopdet, as the herald of the annual inundation. When the star reappeared in the dawn sky after its hidden months, it signaled the approach of the life-giving flood. This connection between a star's rising and the rebirth of the land fused astronomy with religion and agriculture. The ceilings of tombs in the Valley of the Kings bear exquisite celestial maps, meticulously painted with star clocks that divided the night into precise intervals, allowing priests to tell time by observing which deities, personified as star goddesses, crossed the meridian. They believed the souls of pharaohs ascended into the sky to join the imperishable stars of the northern hemisphere, those circumpolar lights that never set, shimmering forever as guardians of the cosmic order. Far across the Mediterranean, Greek thinkers would inherit Babylonian records and transform the interpretation of the heavens from divination to speculation, and eventually to systematic inquiry. Thales of Miletus, gazing at the same constellations that once guided shepherds, became one of the first to suggest that stars might be objects rather than divine symbols, opening the way for rational explanations. His successors, Anaximander, Anaximenes, and later the great Pythagoreans, offered models in which stars were fiery rings, crystalline spheres, or distant suns. The shift in understanding was gradual, but each idea pushed humanity further from myth and closer to something astonishing: the notion that the heavens were governed by consistent principles. When Hipparchus compiled his star catalogue in the 2nd century BCE, noting over 1,000 stars and discovering the precession of the equinoxes through painstaking comparison with earlier records, he demonstrated that the heavens changed not whimsically, but subtly and predictably across centuries. His work would echo nearly 2 millennia later, when modern astronomers confirmed the motions he had sensed in the quiet drift of the celestial sphere. Meanwhile, in China, star studies advanced along a parallel but distinct trajectory. Imperial astronomers, supported by dynastic courts and centuries of precise record-keeping, developed a rich tradition of celestial observation that focused intensely on phenomena we would today call variable stars, novae, and supernovae. Chinese records described the guest stars that flared temporarily in the sky, marking events such as the supernova of 1054, which created the Crab Nebula and remained visible even in daylight for nearly a month. Their catalogues, organized into celestial regions mirroring imperial bureaucracy, reflected a worldview in which cosmic order and imperial stability were intertwined. Astronomers documented every unusual brightness, eclipse, and comet, leaving behind some of the most detailed ancient star observations known, invaluable to modern astrophysics for reconstructing stellar histories. As the centuries unfolded, star lore and star science continued to intertwine across civilizations. The Polynesian navigators, without written language or metal instruments, learned to cross thousands of miles of open ocean, guided purely by the stars, reading the night sky as one might read the surface of familiar terrain. Each island chain was connected by a mental map of rising and setting points of key stars, with names and sequences recited like verses of an oral epic. These master sailors recognized subtle changes in stellar positions, allowing them to weave routes across the Pacific long before Western explorers arrived with sextants. Their knowledge reveals that even without formal astronomy, humans could develop deep intuition about the dynamics of the sky, preserving it as cultural memory passed from navigator to apprentice over generations. During the Middle Ages, while Europe's astronomical progress slowed, the Islamic Golden Age blossomed into one of the most fertile periods of star study in history. Scholars in Baghdad, Damascus, Samarkand, and Cordoba translated Greek texts, corrected them, and advanced them.
Al-Battani refined solar and stellar measurements with extraordinary precision, while Al-Sufi catalogued stars with descriptions of brightness and color that modern astronomers marvel at for their accuracy. The great observatory of Ulugh Beg in Samarkand, with its monumental sextant carved into the ground, allowed observations of intense exactness, and his star catalogue remained one of the most reliable until the age of telescopes. These scholars not only preserved ancient knowledge, but expanded the stellar heritage of humanity, bridging classical antiquity and early modern science.
Then came a moment of profound transformation, the invention of the telescope in the early 17th century. When Galileo Galilei turned his crude but revolutionary instrument toward the sky, he confronted a truth that no ancient observer could have imagined. The soft glow of the Milky Way, long thought to be a kind of celestial cloud or mist, resolved into tens of thousands of faint stars, densely packed and stretching across the heavens like a river of distant suns. Galileo's realization shattered the long-held belief that the universe was modest and human-scaled. Instead, it became vast beyond imagination, studded with a multitude of worlds. His telescope revealed mountains on the moon, moons around Jupiter, and phases of Venus, evidence that Earth was not the center of the cosmos and that the stars might be more than mere points of light, more even than ancient philosophers dared assume. As telescopes improved, so too did humanity's ability to unravel stellar mysteries. By the 18th century, astronomers like William Herschel had begun to measure double stars, believing initially that such pairs were merely optical coincidences. But careful observations over the years revealed that many of these pairs orbited each other, forming binary systems bound by gravity. This discovery indicated that stars were not solitary wanderers, but part of complex families, introducing the idea that the cosmos harbored vast structures and dynamics beyond simple constellations. Herschel's sweeping surveys also hinted that the Milky Way was a flattened disk of stars, with our Sun located not at the center, but embedded within one of its spiral arms, a startling shift in cosmic perspective that challenged millennia of anthropocentric thought. Throughout the 19th century, as human curiosity turned increasingly toward the physical nature of stars, spectroscopy emerged as the key capable of unlocking stellar secrets. When scientists discovered that starlight passed through a prism, displayed dark absorption lines corresponding to specific chemical elements, the revelation was revolutionary. Stars were made of the same elements found on Earth. This shattered the ancient belief that the heavens were composed of a different, perfect substance. Suddenly, stars became approachable, understandable through the laws of physics, and no longer untouchable divine fires. Astronomers like Cecilia Payne would later determine that hydrogen and helium dominated stellar composition, a discovery that turned previous assumptions upside down and laid the foundation for modern astrophysics. By the early 20th century, another profound shift occurred.
Through the work of Ejnar Hertzsprung and Henry Norris Russell, stars were categorized by luminosity and temperature, arranging them along what would become known as the Hertzsprung-Russell diagram, perhaps the most important chart in all of stellar astronomy. This diagram revealed that stars evolved through predictable stages, transforming from collapsing clouds of gas into main sequence objects, and eventually aging into giants, dwarfs, or explosive ends depending on their mass. The narrative of stars became a story of life cycles, governed not by myth or divine influence, but by thermodynamics, fusion processes, and the delicate interplay between gravity and radiation. Stars, once understood as eternal fixtures, now revealed themselves as entities with beginnings, middles, and ends, each shaped by the density of the cloud from which it emerged, each carrying within its luminous heart the story of matter forged in increasingly complex layers. As astrophysicists probed deeper into the thermonuclear mechanisms that powered these immense furnaces, they discovered that the simplicity of hydrogen belied the ferocious processes unfolding inside stellar cores. Observations of variable stars, such as Cepheids, gave astronomers a new cosmic ruler. Henrietta Leavitt's study of their pulsations allowed distances to be measured beyond the boundaries of our own galaxy, expanding the known universe from a solitary island of stars into a vast archipelago of galaxies scattered across cosmic space. With each revelation, stars shifted from objects of distant fascination into indispensable tools for mapping the structure of reality itself. By the time nuclear physics matured in the mid-20th century, the understanding of stellar interiors took another decisive leap. Scientists like Hans Bethe worked out the hydrogen fusion cycle, explaining how stars convert mass into radiant energy through the proton-proton chain and the CNO cycle. These processes, invisible to the human eye and undetectable without advanced mathematics, replaced centuries of speculation with precise descriptions of how stars sustained their brilliance for millions or billions of years. It became clear that the life of a star unfolded on a scale so vast that human civilizations could rise and fall countless times during a single stellar age, making each star not merely an object of study, but a kind of cosmic monument standing silently across the epochs. As research advanced, the strange and dramatic end stages of stellar evolution emerged from the long shadows of misunderstanding. Supernovae, once observed only as mysterious sudden apparitions in the sky, were now recognized as the titanic deaths of massive stars collapsing under their own weight. When such a star exhausted its nuclear fuel, gravity surged unchecked, crushing the core to extraordinary densities and igniting catastrophic explosions that scattered heavy elements across the galaxy. These elements, synthesized in the furious heat of collapsing cores, would eventually seed new star-forming regions, embedding within gas clouds the raw materials for planets, oceans, and life. Thus, the study of dying stars revealed a profound continuity. The iron in human blood, the calcium in bones, the carbon forming the backbone of life's chemistry
All were born in the final moments of ancient stellar lives. The discovery of neutron stars added yet another layer of wonder. These dense remnants, only about 20 kilometers across, yet more massive than the Sun, confounded human intuition. Their existence meant that matter could be compressed beyond anything possible on Earth, forming states where protons and electrons merged into neutrons under pressures unimaginable. When pulsars were detected in 1967 by Jocelyn Bell Burnell, blinking with astonishing regularity, they seemed at first like artificial signals. Instead, they revealed that neutron stars rotated rapidly, sweeping beams of radiation across space like cosmic lighthouses. This realization opened a new era of stellar study, proving that the universe harbored not only beauty, but extremes far beyond human experience. White dwarfs, the remnants of less massive stars, presented a different kind of mystery. When Subramanian Chandrasekhar calculated the maximum mass such objects could attain before collapsing, now known as the Chandrasekhar limit, he laid the foundation for understanding why some stars ended gently while others perished explosively. His insights also paved the way for later discoveries about Type 1a supernovae, whose consistent brightness allowed astronomers to measure vast intergalactic distances with unprecedented accuracy. These explosions eventually led to one of the most shocking realizations in modern cosmology. The expansion of the universe was accelerating, driven by a mysterious energy permeating space. Thus, the study of stars, even in their final acts, provided clues to the destiny of the cosmos itself. Meanwhile, astronomers continued to refine their measurements of stellar populations, texture, and motion. Spectroscopic studies revealed subtle shifts in wavelengths, allowing the velocities of stars to be measured with extraordinary precision. These methods uncovered the existence of dark matter, inferred from the motion of stars around galactic centers. The gravitational influence required to maintain observed orbits far exceeded the mass visible in stars and gas alone. Once again, stars served as messengers, revealing through their movements an invisible framework shaping the universe. As more sensitive instruments were developed, astronomers detected oscillations on the surfaces of stars, stellar seismology, allowing them to probe internal structures and gain insights about density, temperature, and evolutionary stage. Each discovery added depth to the narrative of stars, turning points of light into complex objects with intricate internal lives. Throughout the late 20th century, advancements in space telescopes expanded humanity's reach far beyond atmospheric limits. Instruments like the Hubble Space Telescope revealed stars forming in distant galaxies, captured in crystalline clarity the jets emitted by newborn protostars, and resolved individual stars in globular clusters thousands of light-years away. With these images, astronomers pieced together the early chapters of stellar evolution, observing the birth of stars within dense nebulae where collapsing gas clouds ignited nuclear fusion. Such observations confirmed long-held theories while raising new questions about how magnetic fields, turbulence, and interstellar radiation shaped star formation.
The pillars of creation in the Eagle Nebula, sculpted by winds of massive young stars, became an iconic visual embodiment of this dynamic process, revealing that the birthplaces of stars were far from serene. They were crucibles of energy, radiation, and gravitational conflict. Concurrently, the study of exoplanets added an unexpected layer to the story. When astronomers detected the first planets orbiting sun-like stars in the 1990s, stars transformed from distant suns into potential hosts of diverse planetary systems. Radial velocity measurements, transit observations, and later direct imaging uncovered thousands of planets orbiting stars of all types, from red dwarfs to stellar giants. The realization that planets were common rather than rare fundamentally reshaped the narrative of the galaxy, suggesting that the story of stars was also the story of the environments where life might arise. Each star became a potential cradle for worlds, each system a possible variation of cosmic architecture. Observations revealed planets orbiting pulsars, planets engulfed by red giants, and planets forming within swirling disks of dust around youthful stars. The complexity of these systems hinted at processes of destruction and renewal happening on scales that dwarfed the lifespan of civilizations.
As the 21st century progressed, new observational techniques allowed astronomers to characterize the atmospheres of exoplanets, detect temperature gradients across stars, and even measure stellar magnetic cycles similar to our sun's, but far more intense in many cases. Red dwarf stars, once considered quiet and unremarkable, emerged as hosts of violent flare events capable of stripping atmospheres from close orbiting planets. Conversely, sun-like stars with stable luminosity were increasingly seen as promising locations for habitable worlds. This interplay between stellar behavior and planetary environments underscored the importance of studying stars not just as distant objects, but as engines shaping the evolution of entire systems. Meanwhile, the study of stellar populations in other galaxies expanded dramatically. With large-scale sky surveys like Gaia, astronomers mapped billions of stars in the Milky Way, constructing a three-dimensional atlas of unprecedented detail. This cartography revealed streams of stars left behind by ancient galactic collisions, remnants of dwarf galaxies consumed and absorbed by the Milky Way's gravitational tide. These stellar streams were living fossils of galactic history, and through them, astronomers traced the formation of our galaxy back across billions of years. Some stars, known as population 2 stars and population 3 stars, carried chemical signatures of the earliest epochs following the Big Bang. Population 3 stars, though never directly observed, were theorized to be massive, luminous, and short-lived, forged from primordial hydrogen and helium without heavier elements. Their explosive deaths enriched the early universe with metals, enabling later generations of stars to form planets and eventually life. Gravitational wave astronomy added another dimension entirely. When detectors like LIGO and Virgo captured ripples in space-time produced by the collision of neutron stars, they confirmed theoretical predictions and opened a new observational window on stellar remnants.
These mergers not only produced gravitational waves, but also electromagnetic signals, allowing multi-messenger astronomy to flourish. Observations of kilonova explosions revealed that such mergers were responsible for forging heavy elements like gold and platinum, dispersing them across the galaxy in violent bursts. Thus, the study of stars, even in their most extreme and catastrophic interactions, continued to reveal profound truths about the origins of cosmic material. Black holes, another product of stellar death, emerged as some of the most enigmatic objects in the universe. Theoretical predictions by Carl Schwarzschild during World War I had described them mathematically, but it wasn't until the late 20th and early 21st centuries that observational evidence solidified their place in the stellar narrative. As astronomers detected the X-ray emissions of matter spiraling into stellar mass black holes, and later observed stars whipping around an invisible behemoth at the center of the Milky Way, the realization became inescapable. Supermassive black holes lurked at the hearts of most galaxies, exerting enormous gravitational influence. These colossal entities, millions or billions of times more massive than the Sun, were likely born from the collapse of some of the earliest and most massive stars, and over time fed on gas, dust, and even other stars to reach their astonishing sizes. Their presence added another layer of complexity to the life cycle of stars, linking stellar evolution to the architecture of galaxies. As observations pushed deeper into the cosmos, astronomers began uncovering stars in environments previously considered extreme or even impossible. Hypervelocity stars, for instance, were found hurtling through the galaxy at speeds so great that they would eventually escape the Milky Way entirely. These stellar fugitives were likely ejected by interactions with the galactic center's supermassive black hole, or through violent encounters in dense star clusters. Their trajectories and compositions became valuable clues to the gravitational landscape of the galaxy, mapping invisible contours shaped by dark matter and ancient interactions. Other stellar outliers included magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, which released colossal bursts of energy capable of disrupting satellites from thousands of light years away. These objects represented the extreme boundary of stellar physics, where familiar rules bent under forces so intense that matter behaved in strange and exotic ways. Stellar archaeology, an emerging field devoted to studying the oldest stars, began uncovering relics nearly as old as the universe itself. Some stars in the galactic halo were found to have iron abundances millions of times lower than the Sun's, suggesting they had formed shortly after the first supernovae enriched the primordial gas. These ancient stars served as time capsules, preserving in their atmospheres the chemical fingerprints of the early universe. By analyzing their compositions, astronomers reconstructed the nucleosynthetic processes of the first massive stars and gained insight into the rate of early star formation.
These investigations also revealed that many ancient stars had migrated into the Milky Way from dwarf galaxies long since absorbed, their motions tracing the history of galactic mergers that shaped the modern stellar population. In this way, the study of stars became a form of cosmic anthropology, recovering lost chapters of the galaxy's past. The evolution of star clusters offered yet another rich narrative. Globular clusters, vast spherical collections of hundreds of thousands of stars, orbited the Milky Way like ancient sentinels. Their uniformity in age and composition made them laboratories for studying stellar evolution, revealing how stars aged collectively under similar conditions. Observations uncovered surprising complexities, notably that many globular clusters contained multiple stellar populations with slightly different chemical signatures. This hinted at an intricate formation history, with early generations of massive stars polluting the cluster environment before subsequent stars formed. Meanwhile, open clusters, younger and looser associations of stars, illuminated the early lives of stars like the Sun. The Pleiades, Hyades, and other familiar open clusters became calibration points for measuring stellar ages, anchoring the chronology of the galaxy.
As the search for understanding pushed outward, astronomers investigated stellar nurseries with increasing precision. Molecular clouds, once seen as mere dark patches obscuring background stars, were revealed by radio telescopes to be vast reservoirs of cold gas filled with intricate filaments, clumps, and magnetic structures. Protostars forming within these clouds underwent complex accretion processes, drawing material from surrounding disks that sometimes fragmented into planetary systems. Jets and outflows blasted from their poles, carving cavities in the surrounding medium, while radiation from nearby massive stars could compress or disperse neighboring regions, influencing future star formation. This dynamic interplay demonstrated that stars were both the products of their environments and active participants in shaping them. Observations of triggered star formation, where shock waves from supernovae compressed nearby gas clouds, revealed how generations of stars could be linked through cycles of birth and destruction. The Sun, long familiar yet still full of mysteries, became a focal point of intense study. Spacecraft such as SOHO, SDO, and later Parker Solar Probe revealed the solar atmosphere to be a roiling ocean of magnetic loops, charged particles, and oscillations. The solar wind, an unending stream of charged particles, shaped the heliosphere, a vast bubble surrounding the solar system that shielded it from cosmic rays. Sunspots, solar flares, and coronal mass ejections demonstrated how magnetic cycles influenced space weather, affecting satellite electronics, communication systems, and even power grids on Earth. These studies underscored the importance of understanding stellar activity not merely for scientific curiosity, but for practical considerations in a world increasingly dependent on space-based technology. They also highlighted how even a relatively calm star like the Sun possessed the capacity for dramatic and unpredictable behavior. As computational power grew, numerical simulations transformed stellar astrophysics. Models of stellar interiors, once limited by mathematical approximations, began incorporating complex physics, including convection, rotation, turbulence, and magnetic fields. These simulations produced virtual stars whose lifetimes could be followed from formation to death, revealing details too subtle or too slow to observe directly. Simulated supernovae demonstrated how shock waves propagated through stellar layers, producing distinct chemical signatures and explosive patterns. Simulations of galaxy formation integrated the behavior of millions of stars, showing how stellar feedback regulated the growth of galaxies by heating and dispersing gas. These virtual universes underscored the interconnectedness of stars, not as isolated points of light, but as threads woven into the cosmic tapestry. The discovery of stellar remnants in binary systems unveiled some of the most extraordinary phenomena in astrophysics. In systems where a white dwarf accreted material from a companion star, novae erupted as accumulated hydrogen ignited in runaway nuclear reactions. In more extreme cases, accretion pushed white dwarfs over the Chandrasekhar limit, producing Type A supernovae with consistent luminosity useful for measuring cosmic expansion. X-ray binaries featuring neutron stars or black holes revealed intense gravitational interactions, with matter forming hot accretion disks that emitted powerful radiation. In some systems, gravitational waves carried away energy, causing the orbits to shrink until the remnants merged. These interactions illustrated how stellar evolution was profoundly influenced by companionship, and how dual star systems could produce outcomes far different from isolated stars.
Observations of variable stars continued to deepen scientific understanding. RR Lyrae stars served as standard candles for measuring distances within the Milky Way, enabling astronomers to chart the structure of the galactic halo. Long-period variables like Mira highlighted the late stages of stellar evolution in low-mass stars, revealing how stars shed their outer layers to form planetary nebulae. Massive variable stars, such as Eta Carinae, defied easy classification, experiencing eruptions so powerful that they rivaled supernovae in brightness without fully destroying the star. The complexity of variable star behavior underscored the diversity of pathways a star might experience, depending not only on mass, but on rotation, magnetic activity, and environmental factors. Stars also played a pivotal role in shaping cosmic epochs. The epoch of reionization, when the first stars ignited after hundreds of millions of years of cosmic darkness, transformed the universe into a neutral hydrogen fog, into a transparent medium. These first stars were likely enormous, burning bright and living briefly before exploding as supernovae. Their intense ultraviolet radiation carved ionized bubbles in the surrounding gas, gradually overlapping until the entire universe became permeable to light. Observations of distant quasars and galaxies preserved snapshots of this transition, allowing astronomers to trace the emergence of starlight across cosmic time. The study of these earliest stars revealed not only the beginning of stellar history, but also the dawn of cosmic structure formation. As observational astronomy pushed ever farther back in time, researchers began to detect galaxies so distant that their starlight had traveled more than 13 billion years to reach Earth, effectively allowing astronomers to witness the universe during its youth. These proto-galaxies, chaotic and clumpy, hosted some of the earliest stellar populations, their light reddened and stretched by cosmic expansion. Space telescopes equipped with infrared instruments captured faint glimmers from stars born only a few 100 million years after the Big Bang, revealing a cosmos bustling with energetic activity far earlier than once imagined. Each pinpoint of light in these images represented not merely a star, but often thousands or millions of stars, their collective luminosity illuminating the vast intergalactic medium. This expanding frontier of observation made clear that the history of stars was inseparable from the history of galaxies, each influencing the other's evolution in a continuous, dynamic feedback loop spanning the entire observable universe.
At the same time, the chemical diversity of stars offered a new means of understanding galactic structure. By measuring the abundances of elements such as iron, magnesium, and europium in stellar atmospheres, astronomers developed chemical tagging techniques capable of tracing stars back to their birth environments. This allowed the reconstruction of ancient star clusters long since dispersed and the identification of stellar streams marking the remnants of cannibalized satellite galaxies. Stars with distinct chemical signatures such as enhanced alpha elements or peculiar neutron capture patterns acted as breadcrumbs left across the Milky Way's halo and disk, guiding astronomers toward the forgotten origins of stellar families. These chemical fingerprints revealed not only the contributions of supernovae, but also those of neutron star mergers, each type of event leaving behind a unique elemental imprint. Through this chemical archaeology, the galaxy's past emerged not as a uniform process, but as a tapestry woven from countless individual episodes of star formation, destruction, and migration. Meanwhile, an increasing number of mysterious stellar objects defied simple categorization. Luminous blue variables, for example, underwent unpredictable changes in brightness and mass loss, their unstable stellar winds forming spectacular nebulae around them. Wolf-Rayet stars, massive and short-lived, stripped their outer layers through intense radiation pressure, exposing the hot, fused material beneath. These stars, though rare, played a critical role in enriching the interstellar medium, their powerful winds dispersing heavy elements before the stars exploded as supernovae. Observations also uncovered peculiar objects such as Thorne-Zitkov stars, hypothetical hybrids formed when a neutron star merged with a red supergiant. Although not yet definitively confirmed, candidates showing unusual chemical abundances suggested that nature might indeed produce such exotic configurations. The possibility of these composite stars expanded the boundaries of what stellar evolution could produce under extreme conditions. The study of brown dwarfs further blurred the lines between stars and planets. Initially theorized as failed stars incapable of sustaining hydrogen fusion, brown dwarfs were eventually detected in large numbers through infrared surveys that spotted their faint heat signatures. These objects exhibited atmospheric features reminiscent of gas giant planets, including cloud layers and complex molecular absorption patterns. Their presence filled a previously unrecognized population gap between the smallest stars and the largest planets, illustrating the diversity of objects produced by collapsing gas clouds. Brown dwarfs also formed in binary and multiple systems, occasionally orbiting stars or other brown dwarfs, demonstrating that the processes of fragmentation and collapse operated across a wide range of masses. Their discovery underscored the continuum between stellar and planetary formation, revealing that nature did not always draw sharp boundaries where human classifications preferred them.
Stars in extreme environments provided some of the most astonishing revelations. Near the supermassive black hole at the center of the Milky Way, astronomers observed stars moving at breakneck speeds in highly eccentric orbits, completing revolutions in mere decades. These S-stars, as they became known, traced the gravitational contours of the region, confirming the presence of an object with millions of solar masses compressed into a minuscule volume. Their proximity to such immense gravitational forces made them perfect laboratories for testing general relativity, and observations repeatedly confirmed Einstein's predictions regarding gravitational redshift and orbital precession. The resilience of these stars, surviving in tidal environments strong enough to tear apart less compact objects, highlighted the wide range of conditions under which stellar bodies persisted. As stellar research became increasingly multidisciplinary, astronomers began integrating insights from particle physics, nuclear physics, and quantum mechanics to refine models of stellar behavior. Neutrino detectors, originally built to observe elusive particles emitted by the sun, captured signatures of solar fusion processes in real time, confirming theoretical predictions about energy generation in the solar core. These measurements revealed subtle details about stellar burning and allowed physicists to test the behavior of neutrinos themselves, which oscillated between different types as they traveled from the sun to Earth. Likewise, observations of gamma-ray bursts,
Brief but extraordinarily energetic flashes detected from distant galaxies indicated that some were the final moments of massive stars collapsing into black holes, while others originated from neutron star mergers. These high-energy events provided windows into the most extreme physics imaginable, where stellar evolution intersected with fundamental forces operating at their limits. The diversity of stellar life cycles also played a central role in enriching galaxies with the ingredients necessary for the formation of planets and biological chemistry. Asymptotic giant branch stars, elderly, pulsating stars shedding their material into space, produced carbon, nitrogen, and S-process elements through slow neutron capture. Their gentle winds formed expanding shells of gas and dust, eventually giving rise to planetary nebulae, whose intricate shapes were sculpted by magnetic fields, binary interactions, and stellar rotation. These nebulae, often photographed with spectacular detail, represented the final exhalations of stars like the Sun before they contracted into white dwarfs. Their contributions to the interstellar medium ensured that future generations of stars and planets would contain heavier elements, allowing the cosmic cycle of matter to grow increasingly complex with each passing epoch. As astronomers studied planetary nebulae more closely, they discovered that many displayed astonishing symmetry. Bipolar lobes, concentric rings, and even nested structures resembling ripples frozen in space. These patterns suggested that dying stars often interacted with unseen companions or possessed strong magnetic fields that shaped the flow of expelled gas. Observations from the Hubble Space Telescope revealed features such as fast low ionization emission regions, or FLIRs, that raced away from central stars at peculiar angles, hinting at dynamic processes still not fully understood. These phenomena demonstrated that even in their final stages, stars exhibited remarkable variety and complexity, defying simple models of spherical mass loss and instead producing some of the most visually stunning structures in astronomy. The discovery of stellar coronae explained another long-standing mystery: why the outer atmospheres of stars were often far hotter than their surfaces. In the Sun's case, the corona reached temperatures of millions of degrees, despite the photosphere being only a few thousand degrees. This counterintuitive phenomenon challenged early theories and led to the exploration of magnetic reconnection, where twisted magnetic field lines snapped and reformed, releasing tremendous amounts of energy. Observations of flares and coronal loops across various types of stars revealed that such processes were common throughout the universe, shaping stellar winds, influencing magnetic cycles, and affecting the habitability of nearby planets. Some young stars, rotating rapidly and possessing strong magnetic fields, released flares far more powerful than any observed on the Sun, occasionally producing superflares capable of sterilizing planetary surfaces. Understanding these magnetic processes became crucial for interpreting exoplanetary atmospheres and the likelihood of sustaining life. Stellar populations in dwarf galaxies offered yet another perspective on stellar evolution. These small, faint galaxies, often orbiting larger ones like the Milky Way or Andromeda, hosted stars with extremely low metallicity, similar to those formed early in cosmic history. By studying these stars, astronomers gained insight into how star formation proceeded in environments lacking heavy elements. Some dwarf galaxies displayed bursts of star formation, followed by long periods of dormancy, while others continued forming stars steadily over billions of years. Their chemical compositions often differed significantly from those of larger galaxies, indicating unique evolutionary paths shaped by interactions, supernova feedback, and tidal forces. These galaxies served as natural laboratories for examining how stars formed under conditions unlike those found in the Milky Way, providing clues to the diversity of galactic evolution across the cosmic landscape.
The interplay between stars and their host galaxies became even more intricate as astronomers uncovered the role of feedback mechanisms in regulating star formation. Massive stars, through their intense ultraviolet radiation, stellar winds, and eventual supernovae, injected energy into the surrounding interstellar medium, sometimes compressing nearby clouds to trigger new generations of stars, and at other times dispersing gas so thoroughly that star formation ceased for millions of years. This delicate balance between creation and destruction influenced the morphology and lifespan of galaxies. Spiral galaxies like the Milky Way maintained steady star formation in their arms, where density waves compressed gas clouds, while elliptical galaxies, often the products of mergers, contained older stellar populations whose violent past interactions had heated and depleted their gas reservoirs. These galactic differences highlighted how stars were not merely inhabitants of galaxies, but architects shaping their evolution. The relationship between stellar metallicity and planet formation introduced another layer of complexity. Studies showed that stars with higher metallicity, those containing more elements heavier than helium, were more likely to host rocky planets, since such worlds required solid materials to coalesce from protoplanetary disks. Conversely, stars with extremely low metallicity rarely possessed planet-forming disks massive enough to create Earth-like worlds, suggesting that early generations of stars had little potential for forming complex planetary systems. This realization tied the existence of planets and potentially life to the cumulative chemical enrichment created by successive generations of stars over billions of years. Without the deaths of massive stars scattering metals across vast regions, the universe would remain locked in an era of simple hydrogen and helium, devoid of the ingredients necessary for the diversity seen today. Another realm where stars influenced cosmic evolution was in shaping the intergalactic medium, the vast, sparse expanse between galaxies. Massive stars in early galaxies emitted enormous quantities of ionizing photons, creating bubbles of ionized gas that gradually expanded and merged. This process, occurring during the epoch of reionization, transformed the universe from opaque to transparent. Later generations of stars continued to contribute to this ionization through supernova-driven winds that pushed material out of galaxies and into intergalactic space. Observations of distant quasars revealed absorption lines in the spectra that traced the distribution of these intergalactic elements, offering insights into how far metals had traveled from their stellar origins. The presence of heavy metals even in remote corners of the universe hinted at the extraordinary reach of stellar processes, spreading the ashes of long-dead stars across distances measured in millions of light-years.
As the 21st century progressed, a growing number of peculiar transient events challenged existing models of stellar behavior. Fast radio bursts, millisecond-long pulses of radio energy from distant galaxies, were initially discovered by accident and attributed to exotic phenomena such as magnetar flares or the collapse of neutron stars. Their origins remained a topic of intense debate, with new detections revealing repeating bursts that suggested a wide range of potential sources. Similarly, superluminous supernovae, hundreds of times brighter than typical supernovae, raised questions about the mechanisms powering such enormous luminosities. Some theories posited the birth of rapidly spinning magnetars, whose intense magnetic fields and rotational energy fueled the explosions, while others suggested interactions with dense circumstellar material. These discoveries indicated that the diversity of stellar deaths was greater than previously understood, and that the boundaries of stellar physics were continually being pushed outward by new observations. In addition to dramatic stellar deaths, peculiar stellar births also captured astronomers' attention. Some stars appeared to form not from traditional gas cloud collapse, but through collisions between stars in dense environments like globular clusters. Blue stragglers, unusually young and massive stars found in old stellar populations, defied conventional models of aging. Their existence implied that stellar mergers or mass transfer events rejuvenated them, effectively resetting their evolutionary clocks. These stars offered insights into the dynamic interactions within dense clusters where billions of years of close encounters produced rare and unexpected outcomes. Studying blue stragglers allowed astronomers to understand how stellar populations evolved under crowded conditions and how gravitational encounters influenced the life trajectories of individual stars. Stellar atmospheres themselves revealed complexities that confounded simple models. High-resolution spectroscopy uncovered intricate patterns of convection, granulation, and turbulence on stellar surfaces, while the Sun displayed relatively modest granules formed by convective cells beneath the photosphere. Larger and hotter stars exhibited supergranulation patterns spanning vast areas. Red supergiants, like Betelgeuse, showed irregular brightness changes caused by giant convective cells larger than the distance between Earth and the Sun. These massive, boiling structures transported heat and material through the star's outer layers, influencing mass loss and eventual evolution. Observations of stellar oscillations, minute changes in brightness caused by sound waves traveling through the star, allowed astronomers to build detailed models of internal structure, analogous to how geologists used seismic waves to study Earth's interior. This field of astroseismology opened new frontiers in understanding stellar composition, density, and rotation.
Stellar rotation itself played a crucial role in shaping stellar evolution. While some stars rotated slowly, others spun at dizzying speeds, completing rotations in mere hours. Rapid rotation flattened stars into oblate shapes and caused significant temperature differences between their poles and equators, a phenomenon known as gravity darkening. This altered not only their appearance, but also their internal dynamics, influencing mixing processes that determined how long they remained in various evolutionary stages. Magnetic braking, where stellar winds carried away angular momentum, gradually slowed stars over billions of years, allowing their rotation rates to serve as a kind of cosmic clock, gyrochronology, useful for estimating stellar ages. Young stars, with their intense magnetic activity and rapid spins, exhibited dramatic flares and variable luminosities, while older stars settled into quieter, more predictable patterns. These rotational dynamics highlighted how the life of a star was shaped not only by mass, but by its initial spin and magnetic environment. Binary and multiple star systems continued to reveal new layers of complexity. Around half of all stars existed in pairs or larger groupings, and interactions between close companions often produced dramatic outcomes. Some binaries exchanged mass in delicate streams through Lagrange points, creating accretion disks that glowed brightly in ultraviolet and X-ray wavelengths. Others spiraled closer together due to gravitational wave emission, eventually merging in explosive events. In triple systems, gravitational interactions could trigger Kozai leadoff oscillations, driving eccentricities to extreme values and causing stellar collisions or the ejection of one member. These intricate gravitational dances illustrated how stellar evolution was not always an isolated process, but often a cooperative or chaotic interplay shaped by shared orbits and mutual influence. The study of star clusters in distant galaxies revealed phenomena impossible to observe within the Milky Way. Superstar clusters containing millions of young stars
packed tightly together, shone with brilliance unmatched by any local structure. These environments represented extreme star formation conditions, where gas clouds collapsed into stars with astonishing efficiency. The radiation and winds from massive stars within these clusters carved cavities in surrounding material, sometimes triggering further star formation along compressed edges. Over time, some superstar clusters evolved into globular clusters, while others dissipated due to gravitational interactions with their host galaxies. Observing these structures provided critical insights into how galaxies built their stellar populations during periods of intense activity, such as starbursts triggered by galactic collisions. As telescopes grew more powerful and computational models more refined, the lines between observing, simulating, and theorizing continued to blur. Astronomers began constructing synthetic stellar populations to match observed ones, adjusting parameters such as initial mass functions, star formation rates, and chemical yields to reproduce the characteristics of real galaxies. These synthetic galaxies served as test beds for understanding how different astrophysical processes contributed to the diversity of structures seen in the universe. By comparing models to observations across various wavelengths, from radio to gamma rays, astronomers identified discrepancies that pointed toward new physics or missing processes. This iterative cycle of prediction and observation drove the field forward, continually refining the narrative of how stars formed, lived, and died on cosmic scales.